Okay, this problem involves a car which is heading towards a wall that has a spring on it, and the car's initial velocity is 90 kilometers per hour. And the mass of the car is 1,500 kilograms. Now, the question asks if the maximum deceleration of the car can be 5 g's. In other words, if we take this as being a positive direction, that means the maximum acceleration can be negative 5 g's. Then, if that's true, what is the spring constant K going to be of the car? Now, this is a tricky problem because of this. And the reason it's tricky is that you might assume that you might be able to use a kinematics equation like this one, but you cannot. The reason why this is wrong in this case is because in this problem, the acceleration of the car is not constant. Okay? Therefore, you cannot use these types of constant acceleration kinematics equations. So, what do? Well, let's first of all kind of go through our heads what's happening here. This car is going along, and it now, at this point, touches the spring. Now, what does the free body diagram look like on the car? Well, let's just draw a box here as for the car, and let's say, all right, well, how many forces are on it? There's just one force on the car, and that is the force of the spring, and it's acting in that direction. However, this force of the spring changes. It becomes more and more and more linearly as the spring is compressed. Therefore, if we were to, draw a summation of the forces is F net, that means that the only force is negative SP, because we said this way was positive, and so that's going to equal MA. However, since SP is not constant, A is not constant. So that's the reason why we can't use this. So how do we do this problem? Well, at the maximum location here, let's say it compresses down to this location here. At this maximum location, again, this is what the free body is going to look like. But what is the acceleration at that point? Now, if you think about it, as the box starts to compress, the force gets bigger and bigger and bigger. Well, if you look at this equation, where is the maximum here? Where is acceleration going to be maximum? Well, acceleration is going to be maximum when the force of the spring is maximum. And the force of the spring is going to be maximum when there's maximum compression, therefore at that location. So, that's the location that's going to have the 5 G's. So, what is the force of the spring? It's defined as Kx. What is and X being maximum compression, right? So, on the diagram, let's say this is X max here. Okay? So at this point, basically, the car comes to a stop. Therefore, instead of writing A here, we're just going to put in 5G. Okay, so this is not throughout the entire stopping distance. It is at the last point at maximum compression when the velocity equals 0. Now, if we solve for, now what are we looking for? Obviously, we're looking for k, but we have two unknowns in this problem. We don't know what x is either, and we've only got one equation, so we can't solve it yet. So let's solve for x first. X max is equal to, oh, and by the way, this was a negative. X max is equal to m, negatives go away, 5g all over k. Now, if we now use conservation of energy, we say initial energy equals final energy. Initially, we just have kinetic energy, and finally, we just have elastic potential energy, which is 1/2 kx squared. Now, we can cancel out the 1/2s, and we're going to solve for the k. So if we solve for k, k is going to equal, solving, sorry for the background music there, m v squared divided by x squared. Now, if we come up here and substitute this x into here, oops, way down there, what we're going to get is we're going to have k equals m v squared all over m 5g all over k, and all that squared. So, what are we going to get in total? Well, if you notice here, this m can cancel that m squared. Now, if we just write it out, maybe it might be simpler for the algebra. We're going to get an m squared, 25, a g squared divided by a k squared. And then, of course, this is all equal to k. So let's do a little bit more algebra here, because we're solving for k. So let's just go mv squared times k squared, flip and multiply, m25g squared, and then this m cancels that square, and now this is a k here, and this is going to go to a 1, and then we can get rid of this, and then we're going to have a 25m on this side, g squared divided by v squared, and that's going to equal a k. Now, if we plug in our values, we're going to get 25 times 1,500 kilograms times 9.8 squared divided by 90 over 3.6 squared. And that's what k is going to equal. And if you work that out, we're going to get 25, enter 1,500 times 9.8 squared times 90, enter 3.6 divided by squared divided by, and we're getting an answer of 5,762 newtons per meter. And that's the answer for K. Hope you enjoyed this problem. It was a tricky one. See ya.